This is one of my favorite lectures. In it, in just a few minutes, you will learn how to use phasors to analyze any circuit in which all the sources are sinusoidal and steady state, meaning the sinusoids are always on, there are no switches, but with any number of resistors, capacitors, and inductors. And you'll learn to do all of this within 30 minutes. Let's begin by reviewing last lecture, which was talking about what a phasor is. A phasor is a complex number that represents a sinusoid. Take a look at the sinusoid on our left here. It's a function of time, c cosine omega t plus theta. We can represent that with a single complex number that's a point on the complex plane of the form z, that's how we represent complex numbers in general, is equal to a magnitude of c at an angle of theta. So that's one of the two ways that we can represent a complex number in polar form. We can also represent it in rectangular form. So on our right, we see the complex plane with a real part on the horizontal axis and imaginary part on the vertical axis. I've put a point at our complex number z, and we can represent that as having some distance away from the origin, that's c, and some phase angle. And that single number z, we can completely represent what our time-varying waveform is. And by doing that, we can change our time waveform into a DC, untime-changing waveform. We can change our circuits 2 problem into a circuits 1 problem. Now, last class we learned how to use it to solve simple circuits problems involving only resistors. Here's an example. Now, the problem is to determine the voltage across the current source in this sinusoidal steady state circuit. And by sinusoidal steady state, we mean that all the sources are sinusoids of some type, and steady state means that they've been doing their thing forever. There's no switches in this. The sinusoids aren't being turned on by being multiplied by unit step functions. They're just pure cosines, perhaps at an angle, and pure sines, perhaps at an angle. Now, our first step in solving this is to convert it over from the time domain into the phasor domain. That means if anything is a sine, we're going to have to convert it into a cosine. Same frequency, just subtract 90 degrees. And since all of our sources are currently in cosines, we can just directly write them as phasors. Now we want to find the voltage across the current source. Just notice what we've done again. We've converted these time-changing sinusoids, like 3 cosine of 6t plus 30 degrees, into a single complex number, 3 at an angle of 30 degrees. And by doing so, we've changed this AC time-changing circuit into a DC circuit from circuits 1. In circuits 1, you might have had a voltage source of 3 volts. Well, now it's a complex phasor of 3 at an angle of 30 volts, but it's still just a DC unchanging value. It just happens to now be a complex number. In the same way, we changed our V of t, what we're trying to find, into a single DC value. And we show DC values by capitals, so I changed the lowercase v of t into a capital V. Now that we've changed our circuit from time domain into phasor domain, we can solve using circuits 1 techniques. So we could either solve this using mesh, using nodal, using basic Ohm's law. I'm going to solve it using nodal. And the reason why I'm choosing nodal rather than mesh is if I use mesh, I'll end up finding my currents. But if I end up using nodal, I'll end up finding my voltages. And I'm going to add everything here. To show the new parts I'm adding with nodal, we require a ground. And you'll notice that there's only one unknown node. We know what this node is. It's 3 at an angle of 30 degrees, set by the voltage source. And so the only unknown node here is this one, and we've already called it V. That's the thing we're trying to find. That's the beauty of using nodal for this. We'll just directly find the answer. So there's a single unknown node. We'll have to write a single nodal equation. and we'll do it at V. And we'll say the current traveling to the left through the resistor, which is the voltage across the resistor, divided by the resistance, plus the current going down, which would be minus 2 at an angle of 0. And I hope you can see that 2 at an angle of 0 is 2. Yes, it's a complex number whose imaginary part happens to be 0. Why is 2 at an angle of 0 just 2? Let's draw that complex domain again. Here's the real part. Here's the imaginary part. To draw 2 at an angle of 0, it's got to be, our angle is 0. So there's an angle of 0, and it's 2 units away from the origin. So 2 at an angle of 0 degrees is the same thing as the real number 2. So I'll just draw it. 2. And the sum of those two currents has to be 0. So we've got one equation, one unknown. We don't like these complex fractions. Let's get rid of it by multiplying the top and the bottom by 2. Then we get 2v minus, remember to multiply a phasor, you multiply the magnitude and you don't touch the angle. Now we place our variables on the left, our constants on the right. We divide through by the coefficient of our unknown variable. In this case, we'll divide left and right by 2. And now we'll place it in our calculator and let the calculator do all the difficult work. Remember, for our calculator, we want to set the complex mode to polar, and we want to set the angle to degrees. If you're using one of the TI-89 series or the TI Inspire, you put your complex numbers inside. When you're writing them in polar notation, you put them inside parentheses like this. And you don't have to write the degrees because you already put the calculator in degree mode. And the calculator will evaluate that to be equal to this phasor. And now that you've done that, you can convert it back into the time domain to find the answer as a function of time. And that's the answer using phasors. So now that we've reviewed how to use phasors to solve circuits involving cosines and sines, possibly at angles with sources but only resistors, let's find out how to use phasors to solve circuits that include capacitors and inductors as well.